What is up, everybody? Welcome back to another Nemotron Labs live stream. This is a pretty dope one. We're gonna talk about some routing. We're gonna talk about Devon Switchyard, BAP's channel. I can see this message. Hey guys, please, the whole idea of this is to be interactive for our wonderful experts who we're going to introduce in a little bit. To answer questions that you have. So please throw them in the chat, and we're going to get right into it. I'm going to introduce to you June. We're gonna introduce you a little bit better with a slide and everything. But first, tell us a little bit about what we're talking about today. Model routing. It's a big topic. Give us a lowdown.
Yep. Hey everyone, I'm June. I'm an engineer at Cognition. Today I'll be talking about model routing at Cognition, particularly our hybrid harness called Devon Fusion. We've been working on for the last few months to help our customers save on cost while maintaining frontier quality.
Nice. Okay. Show us what you've been working on, man. Let the good people see.
Okay. Let me share my screen.
Well, it's happening. What is up, everybody? Love to see where everyone's joining from. Slam in the chat where you're joining from. We got people from all over the world today. Excited to learn a little bit about model routing. So, man, if you want to bring up June's screen, let's get this thing going.
Cool. Awesome. Great. Yeah, so today I'll be talking about Devon Fusion and model routing. So at Cognition, we built Devon, which is an autonomous software engineer. And we work with any model provider. So we have a lot of experience evaluating different types of models and thinking deeply about how to improve both the quality and the cost profile of Devon sessions. In this presentation, I want to show you a unique approach to routing we've developed over the last few months, and we call that Devon Fusion. So just to share some motivations, of course, many of the motivations around routing is how do you get the top frontier quality from your models while also saving a lot of cost compared to just using models like Cloud Opus, GPT 5.6 Sol. And for our customers as well, we see rising LLM costs has been a pretty major concern, especially in the last few months. Devon Fusion tries to address both of these issues. One, it orchestrates and pairs various models together in the same session, so you can cut costs while maintaining that frontier level intelligence. And it also, we've evaluated this on high quality benchmarks that evaluate not just can you produce code that works, but also can you produce code that would get merged by a human. So I'll go a little bit more into that later on. But just to give a quick sense of what kind of impact we've seen from Devon Fusion so far, we see that on Frontier Code 1.1, which is the main benchmark we've been using, and it's been highlighted on major model launches like Opus and Fable, we see Fusion being 60% cheaper than frontier models like Opus, while maintaining that frontier performance. And now, in the last 2 months since we've launched Devon Fusion, we see about 1/3 of all Devon sessions being run on Fusion, and this is increasing every day. So just diving into how Devon Fusion actually works. It's a hybrid model harness built right into Devon, and the core idea of Fusion is to pair frontier intelligence together with cheaper and faster, yet still pretty capable models together, working together at the same time, and optimize the collaboration between these models. So you have one lead model and another model that another agent we're calling the Sidekick agent. That work together, and we've really tuned the collaboration between these two so we can optimize both cost and quality at the same time. So there's two factors that make Fusion particularly effective. The first one is that Sidekick architecture I just mentioned, where you have a frontier level lead model and that cost-effective sub-agent called the Sidekick. They're effectively doing pair programming in parallel to be able to execute on the task at a lower cost while maintaining both quality and, in a lot of cases, being able to accomplish the task at a faster speed. And here you basically have at least two models. One is the lead model that's contributing the frontier level judgment that you might find with models like Cloud Opus, GPT Soul, or sometimes even Fable, in tasks like needing to plan how to execute on something, making high quality decisions, and also reviewing the Sidekick's work. And then the Sidekick is basically executing on the lead's plans and doing more of the mechanical work that often costs the frontier model a lot of tokens, even though it's easily doable by cheaper and faster models. And the second factor here is dynamic mid-session routing, which is closer to what you might imagine when you hear the term model routing. So in Fusion, in addition to the Sidekick architecture, we have smart classifiers, which are basically watching the session, not just at the beginning, but also throughout the course of the task to pick the best model for the job, not only for the lead agent, but also for the Sidekick agent. So one thing we find is that to achieve this like frontier level performance, we kind of have to be a little bit conservative in terms of model routing at the beginning of the session, where we don't have all the context about how difficult the task might be. So there we rely more on the Sidekick sub-agent architecture to trust the smart lead model to delegate work as needed. And then as the session progresses, the classifier can get a better sense of, is this a difficult task? Is this a pretty easy task? And do a better job of model routing there. So this, just to dive in a little bit more into how this like Sidekick architecture works. As I mentioned, it's pretty similar to what you might imagine as like pair programming between agents. So unlike most sub-agent implementations, where you have these like ephemeral sub-agents, you spawn once to do one task, and then it kind of goes away and you need to spawn new sub-agents from scratch. The Sidekick has a persistent context, which means the lead model and the Sidekick model can kind of go back and forth. For example, the Sidekick might report some findings up to the lead agent. Lead agent might do some planning, give some task back to the Sidekick, goes back to the lead does some code review, finds some issue, and asks the Sidekick to fix, and on until the lead feels satisfied with the results. And the persistent context means the lead doesn't have to re-explain the entire task every single time it calls on the Sidekick sub-agent. This persistent context also helps us take full advantage of prompt caching to lower the costs. So all the previous context the Sidekick has seen in previous delegations are already cached, and we use a variety of caching techniques to make sure that in the next delegation, all the context can be preserved without that often 10x uncached input costs. So in this paradigm, the lead model, we're trying to basically maximize this so that it can contribute the maximum amount of judgment for this pair programming paradigm, while also minimizing the number of turns that the expensive smart model needs to take, while we're trying to maximize the amount of work that the cheaper and faster Sidekick can do. So this is very carefully tuned because it can be very easy to over-delegate to the Sidekick at a loss of quality. So we've been tuning this on benchmarks like Frontier Code, but also on our internal usage as well as prod usage based on our internal feedback to make sure that we can actually get the same performance as running just the Frontier model on its own, while delegating a lot of the easy work to the Sidekick to save up to 60% costs, especially on types of sessions where you're implementing a PR, for example. So one example is the lead might do some initial exploration on its own, decide like where you need to look, ask the Sidekick to write a report on what it finds in the code base, do some planning, and back and forth until the smarter, more expensive model feels like it has satisfactory results. And because this frontier model is always staying in the loop and reviewing the Sidekick's results, this helps basically minimize any intelligence hit that you might get from incorporating a cheaper but sometimes dumber model into your mixture. Because we often see that if the Sidekick makes a mistake, the lead agent is very reliable in terms of catching those mistakes. And lastly, I also mentioned dynamic mid-session routing as an essential part of Devon Fusion. And the core idea here is that if you pick a model at the start of the task and kind of like never switch models again, you are either likely to be wrong in terms of you chose a model that was not intelligent enough for that task, or you chose a model that was too expensive for most of the task and you're kind of wasting money for at least half the session. So one thing we do is we're continuously watching the session, especially at points where it's cheap to switch models to really find the right model for that stage of the task. For example, initially you need the model and the agent to explore the code base, really figure out, is this a hard task or an easy task, and how should I execute on this? Where we generally conservatively rely more on the expensive frontier models. But later on, once you've kind of figured out most of the task, and you have a better sense of whether that's a difficult task or not, you can route to cheaper models at basically the same performance and much cheaper costs. In Devon, you also have things like once you create a PR, you want your agent to watch CI and respond to any CI failures. And those can be done by much cheaper models than Fable or Opus, for example. So we find model routing to be pretty effective in saving cost, even when you have the Sidekick architecture. And we do a lot of so one thing to watch out for when doing dynamic mid-session routing is cache misses, because in many models, there's a 10x difference between cached input costs and uncached tokens. So sometimes you might switch to a cheaper model, but actually end up paying more because all your context has been cached on the more expensive models. So a lot of our investment here has been into identifying cases where it's okay to switch models. For example, if you are compacting your context anyway, you're already going to incur a cache miss. So that's like one of the best points to reconsider which model to use for your task. But even within, sometimes you might have to wait a long time for your next compaction. So we do a lot of analysis in terms of sometimes it's worth getting a cache miss because the next 20 turns might be able to run on a cheaper model. So there's a lot of basically cost math we have to do here to figure out is this model smart enough for the task, but also is the cost savings going to be worth switching here?
Awesome.
And that's all for me. Let me stop sharing.
Awesome stuff, Jun. Thank you so much. Yeah, I mean, so thanks for setting up kind of the problem space for us, right? And outlining how the folks working on Devon are thinking about this. We're going to bring up a slide to introduce ourselves now, just to let the good people know who we are. So, hey, what's up? My name is Chris. I'm still Chris. I've been here every week. What's going on? I'm joined from my very own team. Real. This is true. Today, please introduce yourself.
Hey, I am Tanay. I work primarily on model evaluations, and my journey for Router began more as an exercise for productizing the insights we generated from deeper evaluations and understanding the strengths and weaknesses of models, and how we went from there.
Very cool. Very cool. You're skipping a lot, selling a little bit short. Today's legend. So thank you for joining us. And of course, Jun, you introduced yourself a little bit, but thank you for walking us through that. So we're gonna take some time to answer some questions now, guys. So if you have any questions about model routing, please just drop them in the chat. We'll try to get to them. We already got a lot, so we're gonna try to rip through these. The first thing we're going to talk about is, listen, okay, I got the green background. I'm not wearing the NVIDIA shirt today, but, I got the NVIDIA title. And so what I want to answer first is, From Jalove Infla, is it possible to route between local and frontier endpoints using something like OpenRouter? I mean, yes, definitely, including but not limited to NeMo Switchyard, which is NVIDIA's library that helps implement router technology. I believe you can even use Switchyard in Devin. This is dope. But Switchyard is kind of like a collection of this technology that helps us to do routing. It's not the only way to do routing, of course, but it's technology that helps us to do it. And the backbone of Switchyard is like a bunch of different algorithms, right? That kind of give us our decision policy, or how do we choose what models to go to in our pool. Tanay, I'd like to hear from you. Like, one of the things that you worked on, a paper accepted to a conference and everything, is this idea of like a prefill router. Tell us how like you think about routing and why something like a prefill router is like a good choice when we're thinking about a question like this. Like, when do I go to this small, fast local model versus when do I go to this like big boy, super intelligent, cloud model? Whenever you're ready.
Oh, yeah. Sorry, a bunch of pop-ups started on my screen. But hey, so I think it's useful to roll back and step back a little bit before we go into specifics of how routers work. So just to level set with everyone, let's say you have model A, model B, and model C. All three of them, let's say, score between 75 to 80% on a benchmark you care about, right? From first principles, uh, what would you want to achieve with routing, right? So the first thing is, of course, all of this accuracy points are achieved with different cost parameters. So you would want to, at the bare minimum, uh, draw a subset of the questions which are answered by all models, and essentially route to the cheapest one in the mix, and then you go on and so forth till you hill climb the accuracy, right? That's one version of it. The other version of it is, which is something we've seen in the rollout, is like not all the models will get the same set of questions right and same set of questions wrong. So 70% for model A and 70% for model B doesn't mean that both of them are equal. They may or may not have complementary capabilities, right? So from a routing perspective, this presents a challenge that you're trying to understand the behavior of the model given the question, right? You're trying to understand whether the model is going to get something right or wrong, and how many turns or how many cost parameters it's going to go to. Furthermore, this is like, if I frame the problem like this, I'm just routing the start of the task, right? I'm ignoring that as the task evolves, like each model has different strengths and weaknesses. So this problem explodes in complexity when you go down in depth. Let's say exploration of search is model A is good. Um, Maybe working in a sandbox, trying to execute code, some other model, and so on and so forth, right? So this becomes very complex in a hurry, right? So one clean way of doing it is maybe use a strong model weak model paradigm, where you accept that, hey, I have a strong frontier model, be it your most favorite accurate model that you have, and then I have a weak cheap model, let's say something like a 30B or of sorts, right? And then you frame the problem as, hey, when I have high certainty in the task, is easy to solve and I can execute. Then you offload it to the weaker quote unquote model, and get the cost savings. And when you have uncertainty, you go to the stronger model. So that is an easy first step to make, which, if you look at any routing software out there, that'll be the first attempt that'll be made, because that's the first place to start. Uh, where you can go from here is you're just trying to understand the model behavior. So it becomes an open-ended evaluations project of sorts, right? And this also speaks to a lot of interpretability work, and that's where our prefill router came in. Um, when you're trying to essentially understand how a model is going to behave, you need something to ground. So let's say you had an evaluation data set for, let's call it a sweet batch, right? Like pick a benchmark. And from there, you have multiple options, right, to do this. First is the simplest thing you can do is take an embedding model, take the prompt, or take the embeddings that an LLM generates, take the prompt, and then just classify by topic. Let's say if we want to reduce this conversation down to, hey, a model is good at coding, a model X model is good at coding, Y model is good at, let's say, tool calling, or pick a domain of your choice. And that's like semantically you're doing topical routing. So if you have a general experts of sort and you fine tune the models on narrow tasks, you can kind of approach it that way, right? The second approach would be to go deeper here and really understand the behavior of the model, right? So maybe at this time I can sort of level set with everyone and say, like, when when you're asking a question to an LLM, there are essentially two things that happen. When you ask the question, there's something called prefill, where your question's encoded into tokens, and the LLM is just trying to understand what you asked. And then there's a decode phase where word by word or token by token, it generates the answer that you have. So at prefill time, you can essentially look at the state of the LLM in its different sort of blocks and streams, and then use that as a signal to understand whether the model is confident towards answering that question or not, or how perplexed it is going to be a marker for how many turns it's going to take to answer those questions. There are different signals to be captured, right? And if you use these signals, you can get a pretty good understanding of how novel the question is to the LLM at hand, right? So there are various techniques of this sort, right? Like where you're just trying to understand at what point a model is confused or perplexed, or does have the capability to answer this question. And this is intimately essentially a recommendation task, which requires deep amount of tuning to your said workload, right? At the end of the day, model A in general will have a performance, and model A in on your workload will have a different kind of performance. So this becomes a tuning task at the end. So we're trying to explore these algorithms as they go. Of course, there are tuning free approaches, like Switchyard has a few, Devin has a few, uh, uh, which are more which are more generalizable and can adapt to workflows. And then you have tuning approaches, or you can even get a middle ground, like you can tune a classifier in a non-tuning approach, and then make those determinations accordingly. Essentially, what you're trying to do is like figure out when to route and what to route to, and that is, on the surface, seems like an easy task, but has taken a few years of the research teams at various labs around the world contributing together to hopefully get a stable state as of now, but we're still progressing.
I mean, I would in fact say it sounds very complicated. It is something that is very hard. And after you click down one level right below, like, well, it's just tossing the request to the right model. It's an incredible engineering challenge, which is why I think most people will interact through routers with technologies like Switchyard, which are implemented in their favorite technology like Hermes or whatever, or like what you see from the presentation that Joon did, which is that this routing strategy is being handled for you when you use the technology, because it is a very complex engineering challenge. Also, of course, hey, Dio, hey, Maxwell MCU, what's up? Welcome to the show. We're talking all things routing. Today, incredible. Thank you. We'll clip that. We'll share it with everybody. Joon, what is the benefit from the kind of Sidekick, like engineered approach that you took? This is from Kurt Warner, by the way. The benefit of doing it this way compared to using just something like Gemini or Claude as your CTO to overview. Like what's the benefit of this strategy versus like I just have my small fast model do all the work, and then I have like Gemini or Claude or whatever just audit it as CTO. Like, what is the advantage to the approach you outlined compared to something like this?
Yep, that's a great question, and there are two answers here in terms of both cost and quality. So there are multiple ways you can do kind of like use a cheaper model to just do everything, and then use a more like frontier model like Gemini, Claude, GPT to review your code. One is kind of in most cases, if you ask a model to review your code, or if you're using a specific AI code reviewer, it'll review the quality of the code, look for bugs, but oftentimes it won't be like deeply considering, was this the right approach to implement this feature, especially if it's a pretty big feature. Another approach is maybe you can optimize for that and just basically prompt the model, like make sure you consider all possible approaches and make sure this is the best one. So the problem with the first one, of course, is you're not really considering the fundamental like approach. Even if you have an expensive model review your code, basically the premise of your change might be wrong, and the expensive model might not catch it either. In the second case, you're basically having the expensive model do a lot more work, basically what it would have done originally if it was in something like the Sidekick architecture, and potentially having to review all of the work. And we see this in terms of cost and speed. If you basically let a cheaper model, let's just say, for example, like GPT 5.6 Luna, just do all the work, in a lot of cases, the whole premise of the change will be wrong. Some other model, let's just say like Opus, might catch these mistakes. It'll have to either redo all of it itself or just give it back to Luna. It can lead to a lot of kind of back and forths that can actually cost more than if you were just having both agents in the loop. And also, even maybe more serious, it'll take maybe like 5 times as long if it's a hard task and a smaller model wasn't good enough to do that particular type of task. So depending on like how you're using these frontier models to do your code review, it can either manifest as a quality loss, or actually just costing more than you would have, possibly even more than if you just use like Gemini or Claude directly.
Yeah, it makes sense, right? It's there are trade-offs with every approach, and some trade-offs are a little bit less desirable than other trade-offs. You know, you don't want to build a whole road and then have someone come in and say, "Yeah, the very nature of this road is fundamentally incorrect." You know, it's a lot of trade-offs to consider, and it just makes a lot of sense. Thanks, June. We had a question from Pavan GP from LinkedIn. How does Nemotron optimize inference efficiency while maintaining model quality? This is not about routing, but wouldn't you know, we did a stream on this last week. Check out YouTube, where we talked with the researchers who built Nemotron, and we talked very specifically about exactly this question. So check out our stream from last week if you want to learn more about that, Pavan. Okay. At the True Shags from YouTube asks, Jude, are there any built-in context management features to help the lead model delegate tasks more intelligently rather than wasting time exploring? This is like a classic question. You know, like, what are we doing to prevent the models from just kind of ambling around?
Yep. So there's 2 parts to this. One is not specific to Devon Fusion, but just in Devon in general. We have a lot of like harness features, prompting to make sure it's basically not spending like 100 turns when 10 turns would have done. This is a pretty like difficult task though. We do see with the latest generation of models, inherently, they do get compared to models you might have seen 6 months ago. We've actually pruned a lot of our like harness and prompts because the models themselves have inherently become better at being efficient. For example, if you compare like GPT 5.5 with 5.6, you might see on the same task, even if they achieve the same score, 5.6 will have spent a lot fewer turns exploring. And it also takes advantage of things like parallel tool calls, or doing multiple batch commands in the same tool call, for example, to achieve this efficiency. But for Devon Fusion specifically, a lot of the leverage here is how do you safely delegate to the cheaper model at different points of exploration without sacrificing quality. And this is a pretty This is something we've had to iterate on quite a lot because exploration seems like a pretty mechanical thing that cheaper models could do. But if you make one wrong decision during your initial planning and investigation, basically the rest of your session might already be predisposed to some wrong approach. So we've done a lot of tuning basically to make sure the lead model only delegates to the Sidekick when a task is clearly like mechanical, but also verifiable by the lead. Just by looking at the results, you can pretty confidently tell, like, do I need to like redo the task, or can I trust the Sidekick's results? So we've been pretty conservative here, which is why we think even though we're already saving up to like 60% of cost on some benchmarks using Devon Fusion, there's actually a lot of room to go way further. For example, if we trained like our own custom Sidekick model, or just as in general as models advance, you could get models that are just as cheap as models we're using in Sidekick today, but maybe, I don't know, like 20% more intelligent. Then not only do you get a higher quality, but also you can save a lot of cost just by saving the number of turns that the more expensive lead model needs to take. But I hope that answered the question.
I think so. I think it, and then some. So I think if you, I mean, it's just the right way to think about it, right? We build models for environments. We are starting to see more and more environments where routing exists in the wild, in frameworks, in agents, and so you can imagine that models are going to get better and better at those workflows. Always an exciting time to continue to realize we are growing these technologies together intimately. Someone mentioned in the comments AVO, which is some recent work by some legends at NVIDIA. We won't be talking about that in this stream, but you can perhaps look forward to something about that in the future on this channel. Today, big question for you, okay? This is from Mr. Real American Values. Love the username in the picture from YouTube. Can you guys talk about how open routing and its impact on subjecting end users to actual task switching? Would you auto-detect types of tasks? It's a bit confusing. How you decide to switch models. It is a bit confusing, right? In fact, even in this conversation, we've talked about many different ways that we could decide to switch models. Which one is best today? How do I think about this? How does Mr. Real American Values think about this?
So, as all things in the world, there's no one best answer. There are trade-offs to make. It largely depends on the size of the application, the velocity of questions coming, and the variety of questions coming. So, for instance, if you want a generic endpoint and like you're just trying to save as much cost that you're trying to achieve, and you don't have an accuracy SLO, then you can make shortcuts and have uh, less complicated algorithms which run pretty light, and make some general estimator. Like just the simplest example you could have, right, is maybe use an LLM to literally judge which question needs to go where, right? Or does the model needs to get routed at all, right? Like at the start of the task, does it seem like a simple question? Yes, no answer. That'll be like a few tokens for a very expensive models, but like still there'll be very few tokens at that, right? So that'll be a simplistic deployment, simple to use, simple to build, simple to scale, right? But the trade-off you're making is you lose control over the logic of the routing completely, because LLM as such is largely a black box that you're shifting your decisions to. And secondly, there's no form of control that you can exert with respect to increasing accuracy there, or is you just get what you get, right? So you can from there go on to an engineered architecture for your application. So for instance, as folks from Devon have built something along the lines, hey, we're doing software engineering, we have a harness, we have studied our problem intimately, and we've designed a solution for it. It's built for a domain that you want to excel at. You want to be extremely accurate. You want to have some trade-offs, but accuracy is the name of the game, and you're building custom build. There are, I want to say, easily over 100 algorithms slash papers discussing about these routing trade-offs, and largely it depends on how much data do you have, how much time you're willing to invest, what are your goals at the end of the day. So yeah, that'd be my general feedback.
Yeah, I mean, guys, a lot of the time on this stream, the answer is it depends, and it's also a very difficult engineering challenge. We're talking about problems that are not solved, right? There is not like a definitive, answer to any of these questions. But I mean, with something like Switchyard, or when you're using Devin, or whatever technology you're using interface with this thing, you can usually find ways to measure it, right? And measuring stuff is just going to be the best way to learn if this is working for you. So how to decide when to switch model? What I'm going to suggest you to do is lean on the experts who are building these things at scale. But if you want to tinker around, hey, there's open libraries like Switchyard. You can play around, and maybe it'll come out with a sweet new algorithm, right? And then we can all benefit from it. And by the way, this is a classic thing I always say in these streams, it seems, but totally unexplored space, guys. We're all learning together. All ideas are great ideas. Sit down with Codex, try something out, measure it. Maybe you'll discover an algorithm that we'll all start using. Okay, it really is that early in the space. Okay. Here is a question I'll answer quickly. Is NeMo Switchyard still an alpha? I believe the answer to that question is it is still being worked on. You should always expect it to be to get better over time. Head over to GitHub to learn exact release status up to date. GUGG29 asks, which model does the routing? Now, this is an interesting question. I'm going to give it to both of you because the answer itself, I think, is indicative of the beautiful and large problem space that is model routing. Maybe we'll start with you, Jun, and then Tanay. Jun, which model does the routing?
Yep. Yeah, that's a great question. So we have multiple layers of this. So like one way is I talked about the dynamic model routing. That type of routing is generally done by a very fast and cheaper model that can classify among many dimensions, for example, task type or difficulty. But the results of that tend to be pretty conservative, where it leans more towards more expensive models than it probably should, because a lot of the times it's pretty hard to detect, especially at the beginning of the task, whether it's truly an easy task or not. Many tasks appear easy, but after some exploration, they actually are found to be pretty hard tasks. But we use faster models, cheaper models in those cases, just to avoid huge cost increase, but also to avoid latency in real prod sessions. But another thing is you can view the Sidekick architecture as another form of a router, where a frontier model is basically dynamically choosing whether it should route the work to itself or a cheaper Sidekick model. And in those cases, we can rely a lot more on the routing results without being too conservative, because you basically have models like Opus, Fable, Sol doing the routing for you rather than a cheaper model. And it also has much more context about the task when it does the routing. So most of the cost savings in Devon Fusion are basically coming from that type of Sidekick delegation, and then another smaller portion from this like dynamic classifier-based model routing.
Makes sense. Today, what model does the routing?
So I'd like to break this question into two parts. It's not. You're essentially trying to solve two tasks with that question. One is what model do I use to decide when do I route, and what model do I use to decide what to route to. It's not as simple like, okay, you're gonna use the same thing. And if let's take the first one, right? Like, what model do I use to decide when to route, right? Now, again, that would be it depends, just like my previous answer. It depends on the routing algorithm, right? As June also mentioned. there may be an LLM as a judge throughout the process, like whether it be a smaller model or a larger model, evaluating its own trajectory or evaluating a third model's trajectory, trying to ascertain whether something went wrong till now, or trying to apply some application logic that was predetermined to be useful. For instance, hey, is this an exploration task? Or hey, is this an execution task? Or hey, is this a search task? Um, or it could be a general classifier that you built. Like for instance, in prefill, we are essentially relying on model weights from a third LLM and a small classifier. Um, I know Route LLM uses embedding models straight out, right? Some models, some routers use MIRT, like just OG just intelligence classification theories. So there's a lot of it depends, right? And similarly, when you're trying to decide which model to route to, the same complexity still arises. You may provide a certain set of business logic where, hey, X topic equal to X Y model, or you use another type of message just yet again to do that, or you build another purpose-built classifier. Now, typically, what happens is purpose-built classifiers are much smaller, and what you're trying to do with them is have some form of feature isolation. So you may use like an embedding model or any kind of encoder from any LLM or any kind of signal apart from that to feed into a classifier of search, whether that be an MLP, an XGBoost, or any other shallow model that also exists, right? So um, it all comes back to how much latency are you willing to take a hit for, and how much granularity of control you want.
I mean, so the answer, which model does the routing, is basically goes all the way from no model to many different models to very strong models to this is again the beauty of the space currently, guys. It depends. It's a very strong it depends here. But I mean, the right thing to think about is trying to, for your task, find the answer to that question, right? Like that's going to be a lot of time. Now, hopefully, technologies like NeMo Switchyard, by the way, help you make that decision faster, but ultimately it's going to be a measurement problem. Today, we're going to do 2 more questions, and then we're going to pay the slide tax. Okay, so today, this is the last question for you from @3WS. We are NVIDIA Inception members routing between local Nemotron, love to see it, and Frontier APIs. Best routing signal, complexity classifier, draft and escalate, or small model logprob confidence, question mark.
Okay, so complexity classifier you can attempt if you wanna, if you have data of any sort for your task. Draft and escalate, if you don't have any data, that's your best bet. Small model logprob confidence. I don't think logprobs are gonna be that helpful for generic agentic tasks, especially for the next tokens. And your strategy is gonna be depending on your inference architecture. If you're doing MDP, you're kind of screwed there even more. So like just in for token artifacts, I don't recommend. Complexities classifier if you have data, draft and escalate if you don't have data. That would be my recommendation.
There you go. You heard it from the man himself. Thank you for the question, and today, thank you for the answer. June, last question for you. Well, not technically last question for you, but I mean last of these flavor questions for you. What about, this is from Kurt Warner again, what about context or drift? When or how does a sub agent stay in check when the project gets big and detailed? I think this is like talking specifically about the sidekick, right? How do you keep that sidekick on track without it spiraling away or just doing what models like to do, which is YOLOing all on its own?
Yep. Yeah, this is a great question. And this was a major issue we saw in earlier prototypes of Devon Fusion that we really had to solve before serving it to customers in prod. There's a couple of things. So one is in earlier, just like more naive prototypes of Devon Fusion, we've seen even frontier models will handle humongous projects to the Sidekick. For example, like migrate this entire code base from C++ to Rust. And of course, like if you're using a cheap enough model, you're probably going to get much worse results than if you were using something like Opus. So we've really had a lot of this actually is guidance on the lead models system prompt, for example, to pick the right size of task. And we really had to tune this because if you go too far here, you might actually see the lead splitting the tasks up too much and basically being a really like micromanager of the Sidekick agent. So you really need to tune the lead's guidance to make sure it has good intuition about when does a task get too large for the Sidekick to handle without enough supervision. So that's one part. The other part is it's pretty risky to, even with the first part, it's pretty risky to just let the Sidekick run for as long as possible without any supervision from the lead model. But on the other hand, you don't want the lead model to be too micromanagey because lead models are expensive. And even just looking at what the Sidekick is doing can cost a lot of expensive turns. So we've had to identify basically how often should the lead check in with the Sidekick if it's taking a really long time and causing too much of a cost increase. And these are both the more we work on this, the more it feels like kind of like the things you learn as like a human engineering manager. You don't want to check in on your reports like too much. How do you really understand what your like Sidekick or engineering report is capable of, and how do you check in just the right amount? So this really depends on the pair of models that you're using for the lead and the Sidekick. The more capable the Sidekick is, for example, if you're using like Fable as the lead and maybe like GPT 5.6 Soul as the Sidekick, they're both very capable models, then you don't really need Fable to check in on Soul as much. But if you're using like Opus as the lead and a really tiny model as the Sidekick, then you might want to make sure you give it small enough tasks and also check in enough to make sure the quality is good. And in a lot of cases, we find that eventually the lead model will find the issues. It's just that if you let the Sidekick go on for too long, your task might take 3 hours instead of 10 minutes. So speed is another dimension we've had to optimize for here. So we've kind of had to tune a lot of the guidance around the lead actually to make sure the Sidekick is receiving the right size of tasks.
There it is, guys. Thank you so much for your question or for your answers today. We're going to pay the slide tax, but before I do want to just say, Runfish asks, is cache prefill solved? Nope, it's not. Still work to do. And then also someone said M Feldman 143 gradient descending the routing. Unironically, yes. These are systems that we can learn. So you bet it's happening. Okay, let's pay the slide tax. Number one, we're going to be in Berlin, guys, for NVIDIA GTC. It's going to be a blast. We're going to talk all things Nemotron and agents and routing and all of the latest and greatest stuff that the teams around NVIDIA have been working on. It'll be a blast. It's in Berlin, end of October. Come on down. We'll be doing a live stream from Berlin, so tune into that if you want to see that, as well as hopefully with some special guests while we're there. Okay, next slide, please. If you heard about this whole agent thing, but you're not quite sure what's going on, please check out our learning paths. These learning paths are going to take you soup to nuts on how to build agents. That's what it is. Okay, next slide, please. If you have any questions or comments or feedback about our NVIDIA Nemotron models, please head over to GitHub. You can learn how to deploy the model, train your own version if you wanted to of Nemotron all through the repo. So head there. Next slide, please. If you want to ask any questions and we're not in the middle of a live stream, or like what happened today, we did not get to your question because there were too many great questions, please head over to our NVIDIA developer Discord and drop the question in hashtag Nemotron models, and we will be able to help you there. Arajit, please, if you want to ask your question in the Discord, we will get to it. So thank you for that. Next question, please, or slide, please. If you want to email our community team, you can do it here at this email address. Zach, our behind-the-scenes legend, all he does is sit in a dark cave answering questions from this email. So please Give him something to do. Give him some company. Email him. This is any questions you have about events, hackathons, stuff like the live stream. Okay. And I think that's it. I think that's all of our slides, which is dope. Let's go. We paid the slide tax. Thank you, everybody. I have one question left for our experts before we let them resume their very busy, very important jobs. We're going to start with Tanay and we will end with Jun. Same question for you both. How the heck did you get into this space, into this very niche part of this very niche space, right? Listen, AI is a big topic, but it's still kind of niche, right? In terms of broad interest. And not only that, this is a very specific part of the field. So today, how'd you get into this?
Yeah, I started my journey while working on model evaluations on this project. So model evaluations in terms of not just accuracy, but like how much does it cost to serve, how much does it cost to complete a task, how reliable is a model, all the dimensions to it, right? And the key marker that we were seeing, hey, like there's not a clear winner in any of these axes. There's a lot of it depends happening, and so what would be the best way to make use of this make use of this it depends? It would be try and build a router to leverage a family of models rather than just getting stuck with one. That would be a sad day where we are relying on one model alone to complete our tasks, because each models will be making their own trade-offs in the development cycle about what they are good at, what they're bad at, what they could work more on. So yeah, that's just the general angle. We took a very evaluation centric angle and then kind of productize our signals into routing.
Very cool. Very cool. Jun, how about you?
Yep.
How'd you get here, man?
Yeah, I think so. Actually, before I joined Cognition, I was at Quora for I think over 7 years. And I was actually an ML engineer there working on recommender systems, where I got my first exposure to ML and AI, things like mixture of experts, etc. And later on in my career at Quora, I was working on Poe, which is like a consumer AI interface where you can get access to all different models. And there I saw a lot of demand from users, it's including like consumers. Like, how do I choose which model should I use? Can you just route all of these for me optimally? And so like I started working on some of the simpler model routing strategies there. Actually, after I joined Cognition just a few months ago, I think one of the first things I did, I think in my 3rd week, was visit customers in Brazil, actually. And I actually like felt kind of this demand for like, how do we get like top quality results, but maybe like, cut the cost by half, for example. And like this cost, LLM costs have been a very hot topic for, I think, basically this whole year. And like visiting customers was kind of like a way to really feel the need for this. Whereas you might not feel it as like internally as much if you work in an org where you are like using the most expensive models, for example. So like when I first joined Cognition, I had a lot of flexibility in what to work on, but that customer trip basically like really motivated me to work on something like Devon Fusion and really try to like maintain that frontier quality and save costs at the same time.
Such a clean answer, right? People wouldn't stop asking you, how do I choose the best model for this task? You're like, I'm going to build something and I'll do it for you, bro. Though, hold my beer. There you go. Guys, thank you so much for your time, for your expertise. Everybody who asked questions or was able to catch the stream today, thank you so much. We weren't able to get to all of the questions, but again, please put them in Discord. If we didn't get to your question live, I'll make sure you get an answer. Just ping me in there. I'm at Chris. There you go. Okay. Thank you so much. And we'll see you next week. Next week, we will see you at 10 a.m. Pacific time, 1 p.m. Eastern Standard Time, or Eastern Time. So we're moving down an hour. Okay. So it'll be 1 hour earlier. We'll see you there. All right. Bye-bye, everybody. Bye-bye, everybody. See ya.